weren't supposed to see that, but I guess I'm working the problem anyway. So this is asking, determine the point on the function. This is optimization. So this is just trying to find the most optimum, the best time where you can either shorten something, make something the smallest, let's say distance in this case, or we can make something the biggest. So in this case, we're determining the point on the function f of x equals the square root of x. So if we remember, that graph looks like this. It is closest to the point 4, 0, which should be somewhere like here. We can pull up the graph of this. We won't get to do this on the exam, but for learning purposes, this is good. So we're basically thinking, if we draw a line at any point on this graph, we draw a line here. When is this line going to be the shortest? So graphically, we can reason, okay, it's probably somewhere around here, but that doesn't really do us much good, somewhere around there. So what we want to do is numerically calculate that. And we can do that by using our distance formula, which says that if we call the distance c, c squared, you know that the distance squared is equal to the final point minus the initial point. So the final point is some x value. So x minus 4 is what we're looking for. X minus 4 squared plus, and we get the 4 because our final point, our final point is on the square root of x. And so the slope, we can do, and then our other one is, so this is just our x value minus our x value from this point. So x, whatever that may be, that's what we're looking for part of. And then minus the y value at that point, plus the subtraction of the y values of both those points squared. So we have plus square root of x minus 0 squared, and that's just going to be x. So if we multiply this out, we get c squared equals x squared minus 8x plus 16, and then plus x. So that's going to look like is c squared equals x squared minus 7x plus 16. So now we can erase this to give us some more room. And now we can find out when the derivative is 0. So that means it has to change from the distance getting smaller to the distance getting bigger. So if we look back at our graph, and this distance keeps getting smaller as we go to the right, then at some point around here, we get the closest we're going to be. That's what we're trying to find, that point. This might not be accurate, but it's somewhere around here. And then it starts getting farther away. So this is like a derivative. This distance goes from getting smaller to then getting bigger. So the derivative goes from negative to positive. So we turn this into a derivative problem. So if we take the derivative of this, we get 2c times dc dt, or no, dc dx equals 2x minus 7. So then we know that dc over dx equals 2x minus 7 over 2c. And then we know that this is 0. What we want to find when dc dx is 0. So we have 2x minus 7 over 2c equals 0. And the distance is not going to be 0, so c, we can't plug in 0 at the bottom as one of our points. So we have to plug in when the numerator here is 0. So that happens when 2x minus 7 equals 0, and that happens at x equals 7 over 2. So if we look at our answer choices, only one of those has that, but let's finish it off. Now we have at x equals 7/2, the derivative is 0. So that means that's when it goes from getting closer and closer to farther and farther. And now we plug this back into the original function to find the y value. So f of 7/2. And then since this is just the square root of whatever our plugged in value is, then it's just the square root of 7/2. And we end up with b. So this is kind of similar to related rates in the way that you go about doing it. You think about what general formula can show the relationship between these two values. And and you can find when you're getting closer and then farther by setting the derivative equal to 0, kind of like related rates. And after optimization, that is unit 5.